Hi everyone, in the last lesson we talked about enantiomers, diastereomers and meso compounds. In this lesson we are going to combine those things and we are going to use it to determine optical activity. Right, so the key points behind determining optical activity is that the shape of the reactant molecule, right, or the intermediate, right, affects the ability of the product mixture to rotate plane polarized light. Notice what I'm concerned here is the product mixture. Okay, I'm not just interested in the product, I'm interested in the mixture itself. Okay, why is that so? Alright, it's because sometimes you might have racemic mixture, sometimes you might have the pure enantiomers present. Okay, so the questions that we want to ask ourselves is, does the molecule contain a chiral carbon? Right, does it have an internal plane of symmetry? Is it a racemic mixture? Because all these 3 points will not. Alright, rotate, plane, polarize, light. Right, so let's take a look at these few examples here. So we know that the structure, right, or rather the shape of this ketone here is trigonal planar, right? So it is flat, right? And because it is flat, the CN group, right, the CN nucleophile can either attack from the top or attack from the bottom at 50-50 chance. Alright, so this means that the final product will have an equal mix of both enantiomers, therefore it gives you a racemic mixture. Alright, but first and foremost, alright, we need to draw the products first. Right, so if it attacks from the top and bottom, right, my final product will look like that. Okay, of course, I have I have omitted HCN as the other reagent. Okay, and I will also get this as my product. And what you can realize is, even if it is not flat, right, it does not contain a chiral carbon because two of these groups are exactly the same. They are both the methyl groups, right? So this molecule does not have a chiral carbon. So because it doesn't have a chiral carbon, right, it is unable to rotate plane polarized light. But even if it contains a chiral carbon at the end, let's say I change this to instead change this to R1 and R2. Okay, if I have R1 here, R2 here, R1, R2, right, you will get a chiral carbon, but because it is both of these are present in 50-50 ratio or 1:1 ratio, right, it will not rotate plane polarized light. So another example is this nucleophilic substitution SN2 mechanism. Alright, so in this SN2 mechanism, I'm going to kick this group out. Okay, and what I will see is that I will get an inversion of configuration. Right, I'll have my R2, R1 here. Alright, and this has a chiral carbon, it is a pure enantiomer, it will be able to rotate plane polarized light. So for the other example, it also does the same thing, it's able to show you an inversion of configuration. However, you have two similar groups here. So no, once again, like the previous case in our ketone, alright, we know that there is no chiral carbon, alright, there's no chiral carbon at all. So because there's no chiral center, it will not exhibit the ability to rotate plane polarized light. So just take note, just to reiterate again, alright, if the product does not have a chiral carbon, it will not rotate plane polarized light. If the product has an internal plane of symmetry, it will not rotate plane polarized light. And if the product is a racemic mixture, right, which comes from planar molecules or intermediate, it will give you it will also not rotate plane polarized light. Alright, so this is how you can determine if a reaction will give you product mixture that would give you an optical activity.